We're going to find the equations for the currents I sub R1, I sub L, and I sub R2 for t greater than 0. We need to follow these steps. If for t greater than 0 no source is connected, then the solution will be of the form of the natural response. That means that I sub R sub 1 is going to be equal to a e to the minus t over tau for t greater than 0. And I sub R sub 2 will also be of the form of the natural response, b equal to e to the minus t divided by tau for t greater than 0. And I sub L will also be an equation similar to the natural response. We notice that all these equations have the same tau, where tau is the equivalent inductance divided by the equivalent resistance. Then, to determine these equations, we need to find the values for A, B, and C. And in order to do that, we will perform circuit analysis at time t less than 0, t equals 0, and t greater than 0. Let's start by doing the circuit analysis at t less than 0. First step is to inspect the sources and see which ones are connected. We can see that the 12-volt source is connected, and we say that that is on because the switch is on for t less than 0. We need to check the status of the inductor, and we know that inductors connected for a long time to DC sources will be like short circuits. And with this information, we redraw the circuit, the voltage source, followed by the resistor, the inductor being a short circuit, the two resistors on the last branch, 4, 5, 7 ohms, the currents that we need to find, I sub R sub 1, I sub L, and I sub R sub 2. We see that the current flows out of the source to the upper node. Now we need to determine which way that current will flow. We have one branch with 7 plus 5 ohms and another branch that is a short circuit with 0 ohms. So it's going to flow through the inductor. No current is going to flow through the resistors. So we write I sub x is equal to 12 divided by 4 ohms equal 3 amps. So for t less than 0, the currents I sub R1 will be 3 amps, I sub L will be 3 amps, and I sub R2 will be equal to 0. Then we have to check the status of the inductor. We know that in time less than 0, the inductor was charged with a current of 3 amps. At the instant that the switch turns off, the energy in the inductor cannot be dissipated in 0 time. So we write that I sub L of 0 plus must be equal to I sub L of 0 minus, and that should be equal to 3 amps. Energy stored in the inductor is going to act as a current source in our analysis at t equals 0. Then let's redraw the circuit. The switch is off. We have the inductor as a 3 amp source and the resistors 4, 5, and 7 ohms. The currents that we need, I sub R, I sub L, and I sub R2. We can see that current I sub R1 is 0 because the switch is off. The only current that flows is the current from the inductor. So for t equals 0, I sub R sub 1 of 0 plus is going to be 0, I sub L of 0 plus is going to be 3 amps, and I sub R2 is equal to minus 3 since the current flows in the opposite direction of the flow of the inductor current. Now, the analysis at t greater than 0. Since no source is connected for t greater than 0, we know that all the currents and the voltage on this circuit are going to be equal to 0 after phi time constant, or after phi tau. So we need to find the value of this time constant, or tau. In order to find tau, we need to remove the sources from the net. We need to mark across the terminals of the inductor X and Y. We remove the inductor from the circuit. And now we're going to try to find the equivalent resistance across X and Y. And we see that we have a 5 ohm resistor followed by a 7 ohm resistor. We go around the loop, that is 12 ohms. So tau is L equivalent divided by R equivalent, 4 henries divided by 12 ohms, that's 1 divided by 3 seconds. Since we have all the values for t less than 0, t equals 0 and t greater than 0 for all the currents. Now we're going to determine the equations for each one of these currents. So the general equation of the natural response is f sub t is equal to a variable a, times e to the minus t over tau for t greater than 0. So the equation for I sub r1 is going to be a times e to the minus t over tau for t greater than 0. To find the value of a, we do analysis at t equals 0, and at t equals 0, I sub r1 is equal to a times exponential to the 0, that is 1. Then a is equal to the initial condition of the current, r sub 1. And current r sub 1 at 0 plus is equal to 0. So I sub r sub 1, the equation is going to be 0 for t greater than 0. The equation for I sub L, again, is of the form of the natural response, so it's going to be I sub L equal to b e to the minus t over tau for t greater than 0. To find b, we do the analysis at t equals 0, and we set that I sub L sub 0 is equal to b exponential to the 0, where b is just the initial condition of I sub L at 0 plus. That initial condition is 3. So our equation for I sub L sub t is equal to 3e to the minus t over tau for t greater than 0. Now, for I sub r2, again, the general form of the natural response is I sub r2 is equal to c e to the minus t over tau for t greater than 0. We find the value of c at t equals 0. That c is going to be equal to the initial condition of the current I sub r2 at 0 plus. That value is equal to minus 3, and so we write the equation I sub r sub 2 is equal to minus 3 e to the minus t divided by tau for t greater than 0. And these are the three equations for the currents on the circuit.